all the matter that exists in the universe, from the stars above to the iron in your blood. The oxygen you breathe and the hydrogen in every drop of water originates from the same cosmic source. But where is that place? For centuries, humans have gazed at the sky, wondering about our origins and destiny. We once believed the universe was a fixed dome of lights above a motionless Earth. Then we learned those lights were suns scattered across unimaginable distances. But the most astonishing revelation came later. Most of the universe cannot be seen. Everything you see, the mountains, the oceans, your body, the stars, barely represents a tiny part of what exists. The visible universe, comprising billions of galaxies and trillions of planets, is merely a thin layer atop an invisible ocean. The matter we are made of, atoms, molecules, chemical elements, makes up less than 5% of everything the universe is made of. And what about the other, almost 95%? Where is it? The rest of the components of the universe are there, but we can't see them with our eyes, yet they shape the very fabric of the cosmos. From a mysterious force that stretches space to a substance that holds galaxies together, the most abundant components of the universe are also the most enigmatic. We live within a fabric that we barely understand, surrounded by what we cannot see or touch. But thanks to our technology and intelligence, we have developed methods to detect what is invisible to our limited senses. The most abundant matter isn't found on Earth, and the most powerful energy isn't the brightest. It's the one we cannot see. What's truly normal in the universe is far from what we experience on Earth. Soil, air, and water, so familiar to us, are rare elsewhere. Even more astonishing, within that tiny visible fraction of the universe, an even smaller sliver has organized itself into life, thought, and consciousness. This is not a journey to look outwards, but inwards of the cosmos itself, towards its invisible components, its hidden laws, its reason for being. From the particles that make up matter to the energy that expands the universe. From the invisible that holds galaxies together to the instant when the universe began to think about itself. Get ready to explore what the universe is truly made of. Imagine you're holding an apple. If you cut it in half, and then cut it again and again, there will come a time when the knife can no longer move forward. But suppose we have a knife thin enough that it can cut even the smallest thing. What would be left then if we continue cutting? Carl Sagan said that if we could continue to divide eternally, we would discover the secret of the universe. Atoms. And within them, we find the subatomic particles that make up everything that exists. Everything we see, from a star to a dewdrop, is built with the same invisible pieces. In the first moments after the Big Bang, the universe was a fiery soup of pure energy. From that energy, through a process called mass-energy conversion, the first fundamental particles emerged. It was the first act of physical creation, light transforming into matter. Among those particles, three essential protagonists appeared: protons, neutrons, and electrons. Protons have a positive charge, electrons, negative charge, and neutrons, as the name suggests, are neutral. The dance of these three particles defines the structure of everything that exists, what has existed, and what will exist. A proton can attract an electron with such an intense force that even separated by a microscopic distance, they remain bound by the invisible electric force of the universe. However, those are not the final pieces. Protons and neutrons are made up of even smaller entities called quarks. These are grouped into trios and held together by a colossal force mediated by particles called gluons. Electrons, on the other hand, belong to another family, leptons, which are not made up of quarks. Together, quarks and leptons are the building blocks of matter. Bosons, messengers of the fundamental forces, operate around it. The photon carries the electromagnetic force. The W and Z bosons govern the weak nuclear force, and gluons hold quarks together inside protons and neutrons, while the residual strong force binds protons and neutrons within the nucleus. According to the standard model of particle physics, the entire universe, every star, every oxygen atom, every cell in our body, arises from the interaction of these invisible entities. But there is a more profound mystery. If all particles were born without mass, why do some weigh more than others? The answer lies in an invisible ocean that permeates everything: the Higgs field. When a particle moves through this field, it interacts with it and acquires mass, as if swimming in an invisible cosmic fluid. In 2012, CERN scientists confirmed its existence by detecting the Higgs boson, the tangible fingerprint of this universal field. As the universe expanded and cooled over millions of years, these particles began to fuse. Protons and neutrons formed nuclei, and electrons orbited them. Thus, the first hydrogen and helium atoms were born, the seeds of the cosmos. From that primitive chaos came order. From energy, matter. And of the subatomic particles, the particle of which everything would be made, the atom. Each atom is a masterpiece of balance. At its center resides a tiny nucleus made up of protons and neutrons, so dense that if an atom were the size of a cathedral, that nucleus would be just a grain of rice suspended in the middle of the vacuum. Around them, electrons move in a continuous dance, contained by the electrical pull of the nucleus. That dance holds the universe together. The combination of the number of protons defines the identity of each atom. A single proton means hydrogen. 2 means helium. 8 means oxygen. All the elements that exist, from the air we breathe to the iron that runs through our blood, arise from this simple principle. Varying the number of particles in a nucleus changes the nature of everything we know. But atoms alone are not enough. In the universe, atoms tend to stick together. When 2 or more atoms share electrons and bond, molecules are born, the first structures that shape solid, liquid, and gaseous matter. Water, for example, is the union of 2 hydrogen atoms and 1 oxygen atom, a bond so stable that it covers 3/4 of our planet and sustains all life. The beauty of atoms lies in their versatility. They not only build the small, but also the immeasurable. From a grain of sand to the most gigantic galaxy. Everything we can see with our eyes is made of atoms. Everything we perceive is the result of atoms interacting, vibrating, colliding, or sharing their charge. Even the heat we feel when we touch a stone under the sun is nothing more than the frenetic movement of the atoms inside it. And yet, the universe was not satisfied with a single type of matter. From these simple units, a cosmic alchemy was unleashed that billions of years later would fill the sky with colors and planets. The atoms were the first notes in the symphony of creation, but the major chords were still missing. The chemical elements, which would be born in the incandescent depths of the stars. When atoms were born, the universe was filled with possibilities, but also with monotony. At first, there were only the three simplest elements: hydrogen, helium, and a trace of lithium. For hundreds of millions of years, that uniform mixture floated in the dark, until gravity concentrated it into huge clouds that collapsed under their own weight. And then, for the first time, the cosmos saw the light. The first stars were born. These stars ushered in a new era, the era of cosmic alchemy. Over billions of years, the first stars began to cook up the main ingredients from which the others would form. In the nuclei of stars, the atoms began to fuse, transforming hydrogen into helium and helium into heavier elements. Each reaction released an immense amount of energy, which kept the star alive in a perfect balance between radiation and thermal pressure from fusion and gravitational collapse. This nuclear force keeps stars alive through constant expansion, a process slowed and controlled by gravity, which pulls them toward their centers. When stars exhaust their fuel, hydrogen and helium, they start burning other elements. It is precisely at this point that gravity gains strength, leading to the star's death in a massive explosion known as a supernova. In this death, the star releases all the materials it formed throughout its life, which are dispersed in a supernova remnant, which will later be the nursery where the next generation of stars will form. This new generation will have planets around them made from the remains of the elements that formed the first stars. The calcium in your bones, the oxygen you breathe, and the hydrogen in the water you drink, all the elements that make up life, emerged from the life and death of stars. That's why Carl Sagan said, "We are stardust." What we call today the periodic table of chemical elements is nothing more than the inventory of what the stars manufactured and continue to manufacture today. For centuries, humans have sought to understand the underlying order behind this variety. In the 19th century, Russian chemist Dmitry Mendeleev imagined a way to organize the elements by their atomic properties and masses. His table not only predicted elements that were not yet known, but reflected a more profound truth. Matter was not chaos, but a structure with symmetry. But the cosmic history of these elements was revealed much later, in the 20th century. Astronomer Cecilia Payne-Gaposchkin found that the sun and stars were composed primarily of hydrogen and helium, challenging the belief that they were similar to Earth. And later, the astrophysicist Fred Hoyle proposed that heavy elements formed in dying stars, in cataclysms that we now call supernovae. When a massive star explodes, it blasts the atoms it created into space, seeding new clouds of gas with the ingredients of future worlds, the nebulae. Over time, those element-rich clouds condensed again, forming planets. Thus, the periodic table is not only a scientific tool, but a cosmic poem, the record of how the universe transformed simplicity into complexity, energy into form, chaos into life. The stars were the first alchemists. We are his conscious legacy, a testament to the self-awareness he cultivated. However, among the known matter that we can perceive with our senses, there was hidden type of matter that we could not see at all. This type of material would be the great discovery of the 20th century: antimatter. Everything in the universe has a reflection, an inverted image that seems to obey the same laws, but in reverse. At the beginning of the 20th century, physicists discovered that nature not only manufactures matter, but also its exact opposite, antimatter. Although both are almost identical, their collision destroys them, releasing pure energy. The concept was born in 1928, when British physicist Paul Dirac tried to unite quantum mechanics with Einstein's theory of relativity. From his equations came a surprising idea. For every particle of matter, there must be another with the same mass, but with an opposite charge. The following year, experiments confirmed his intuition. The positron, the twin of the electron, but with a positive charge, appeared. It was the first objective evidence that the universe had a hidden mirror. Just as the electron has its positron, the proton has an antiproton, and the neutron an antineutron. Suppose a single particle of matter encounters its antimatter counterpart. In that case, they both disappear in a fraction of a second, releasing a burst of energy thousands of times more potent than a chemical reaction. That total conversion of mass into energy is reflected in the equation, formulated by Albert Einstein. But this finding left scientists with a perplexing question. If the Big Bang created matter and antimatter in equal amounts, why is the visible universe made almost entirely of matter? Where is its reflection? Where did all the antimatter go? According to the laws of physics, both should have annihilated each other in the first instance of the cosmos, leaving only radiation. And yet, something broke that perfect symmetry. A slight difference, perhaps a quantum fluctuation or a minuscule violation in fundamental laws, allowed an infinitesimal part of matter to survive. That tiny fraction, one particle in a billion, was enough to form everything that exists today: galaxies, planets, and life. Antimatter, on the other hand, almost disappeared. Today, we only find it in cosmic rays, or it is artificially created in particle accelerators such as CERN, where protons are propelled to speeds close to the speed of light and collide, recreating the conditions of the early universe. It is so ephemeral and so challenging to store that just a few micrograms would be enough to destroy an entire spacecraft if all its energy were released. The matter that composes us, the so-called baryonic matter, since it is composed of baryons, is therefore a cosmic rarity. A fortunate accident in a universe that seemed designed for annihilation. Perhaps the greatest mystery of the cosmos is not what exists, but what is missing. And in that absent emptiness, in the shadow of what was not, lies the answer to our own existence. When we looked at the cosmos, we realized that what we are made of is not the same as what most of the universe is made of. In fact, 99% of the universe is made of something different from what human beings are made of. Plasma. Everything visible vibrates, burns, shines. Matter in its most common state is neither solid nor liquid. It is fire. On Earth, human beings live with rocks, water, and air, and we tend to think that these three states, solid, liquid, and gaseous, are the ones that dominate the universe. But outside of this small blue planet, the rules change dramatically. Out there, more than 99% of the baryonic matter in the cosmos is in a different state than the three most common on our planet. Plasma. Plasma, also called the fourth state of matter, is the one in which atoms decay and release their electrons, leaving an ocean of charged particles that respond to magnetism and electricity. It is a state so extreme that it belongs neither to the solid nor to the gaseous world, but to a frontier where matter and energy seem to merge. Some things we live with in this state include fire and lightning. Every flash of lightning we observe in the sky is a manifestation of plasma. Excited clouds that radiate light, lightning that tears through the Earth's atmosphere, auroras dancing at the poles, painting the sky with solar particles trapped by our planet's magnetic field. In all of them, matter is temporarily converted into visible energy. It is also the state in which stars, nebulae, and galaxy clusters are found. At the heart of the Sun, plasma reaches temperatures of millions of degrees. Protons move so fast that they can fuse, transforming a tiny fraction of their mass into light and heat. That light travels for thousands of years until it escapes the solar surface, and then another 8 minutes until it reaches Earth, where it warms oceans, moves winds, and awakens life. Every photon that illuminates a flower or a human face was born in that distant fire, in an ocean of plasma that knows no rest. When scientists look at the cosmos, they understand that the solids and liquids around us are exceptions, not the rule. The normal thing in the universe is the glow, the matter on fire. Plasma is the natural form of matter and the universe. We can say, without exaggeration, that we live on an island of cold matter within a fiery ocean. All that shines in the sky is plasma. Everything that does not shine is made of the ashes of that fire. We are the ashes of the cosmos. Matter doesn't just build the universe, it illuminates it. But what shines is not all that exists, because the universe, although it shines, is also made of what we cannot see. And in that darkness, in that invisible silence, lies the next great mystery: the dark matter. In the 1930s, when astronomy was still a young science and the universe seemed almost domesticated, an eccentric Swiss-German astronomer began to notice something that no one else saw. His name was Fritz Zwicky, and he worked at the Mount Wilson Observatory in California. Zwicky was brilliant, but also unpredictable. He challenged theories, argued with colleagues, and refused to accept comfortable truths. And in 1933, it was he who lit the first spark of a mystery that still baffles science today: dark matter. Zwicky was studying the Coma Cluster, a vast congregation of galaxies more than 300 million light-years from Earth. With the most powerful telescopes of his time, he measured the speed at which those galaxies orbited around the center of the cluster. According to Newton's laws of gravity, those speeds were to be determined by the amount of visible matter, stars, gas, and dust. But when he did the math, something didn't click. Galaxies were moving too fast. The hypothesis was that if only the visible matter existed, the cluster would have exploded long ago, scattering its galaxies through space. But he didn't. Zwicky concluded that there must be something more hidden, an invisible, unknown mass that exerted enough gravity to hold everything together. He called it dunkle Materie, that is, dark matter. Zwicky then made a calculation that would change history. He estimated that the visible mass of the cluster was not enough to explain its stability, and that there must be about 400 times more invisible mass than visible. In other words, only a small fraction of the total was luminous matter. His estimate was equivalent to saying that only a few percent of the cluster's mass was visible, while the rest, 99%, belonged to an obscure and unknown substance. Today, we know that his calculation was an overestimate, since baryonic matter, that which we can see, that which is composed of subatomic particles and forms planets, stars, living beings, antimatter, and plasma, makes up only 4.9% of the universe, while dark matter, that which we cannot see, makes up about 27%. Yet his intuition that most matter was unseen proved right. Zwicky, without modern instruments or computers, had intuited almost a century earlier the essential proportion of the cosmos. But in 1933, his idea was ignored. Astronomers of his time scoffed at his hypothesis. How could there be a dark matter that no one saw, and that was based on a simple mathematical calculation? Most considered it a miscalculation or an extravagance of his temperament. Zwicky was sure, though. He had seen something that did not shine, but that manifested itself through gravity. He died in 1974, without recognition, but his discovery would be claimed decades later, when new observations confirmed his suspicion. For decades, Zwicky's warning was forgotten. The universe continued to be studied through its light: stars, nebulae, galaxies. But gradually, astronomers began to notice an eerie pattern. Visible matter did not correctly explain the behavior of the cosmos. Something else, something invisible, influenced all bodies. The first big clue came in the 1970s from American astronomer Vera Rubin, who studied how spiral galaxies rotated. According to Newton's laws, stars farther from the galactic center should orbit more slowly, just as the outer planets of the solar system orbit the Sun more slowly than the inner ones. This is based on the principle of gravitational attraction. The farther away two bodies are, the weaker the gravitational attraction between them. But Rubin observed something unusual. The stars at the edges of galaxies were spinning at the same speed as those at the center. It was impossible. If only luminous matter existed, those galaxies would have broken up millions of years ago. The only explanation was that they were immersed in an invisible mass, a kind of halo that held them together. Later, modern telescopes confirmed another phenomenon predicted by Einstein: gravitational lensing. Gravity, when intense enough, bends the path of light. Thus, a large concentration of mass, even invisible, can distort the image of objects further away, as if space itself were a curved lens. In many observations, astronomers detected these distortions without finding a light source capable of causing them. The conclusion was inevitable. There was matter that was there, but that we could not see. As technology advanced, cosmological simulations revealed that the large-scale structure of the universe, the immense network of filaments that connects galaxies and clusters, could not form without the gravitational weight of dark matter. It is what molds the skeleton of the cosmos, the invisible framework on which visible matter accumulates. Without their presence, the universe would be a scattered chaos without galaxies or stars. And then came one of the most conclusive pieces of evidence: the bullet cluster. In this collision of two galaxy clusters, the telescopes detected that most of the mass did not coincide with the bright gas that emitted X-rays, but was displaced, as if visible matter had been moved away from the true center of gravity. It was a cosmic X-ray of the invisible universe. Today, the evidence is overwhelming. We know that dark matter does not emit light, does not reflect or absorb electromagnetic radiation, does not interact in any way with ordinary or baryonic matter, but its gravity betrays its presence. It is the scaffolding of the cosmos, the glue that holds everything together. And yet, despite all the evidence, no one has been able to see it directly. We know it's there, but we don't know what it is. The universe seems to be mostly made of something we can't see at all. Then the question arises: what is dark matter? So far, everything we have described, atoms, stars, galaxies, belongs to the same kingdom, that of baryonic matter, ordinary matter. The one that you, me, the Earth, the Sun, and the galaxies are made of. Even antimatter, that matter that annihilates on contact with ordinary matter, is in this category. All that matter is part of the same framework. It is composed of identical particles, only with opposite charge. But dark matter is another story. It has nothing to do with matter, much less with antimatter. It does not shine, reflect light, or emit radiation. Unlike antimatter, it does not interact with ordinary matter. Moreover, it cannot be touched, and we cannot contain it. It is a type of substance completely different from anything we know, invisible even to the most sensitive detectors. We cannot see, feel, smell, taste, or hear it. And yet we know it exists because we can measure and observe its gravitational influence throughout the universe. Its strength is as real as that of any planet or star, but its nature remains a mystery. For decades, physicists have been trying to figure out what it might be. One of the most solid hypotheses is the so-called weakly interacting massive particles. Massive particles that would interact very little with ordinary matter, except through gravity. If they exist, they would be thousands of times heavier than a proton and would traverse the Earth constantly, leaving no trace. Another possibility is axions, tiny and very light particles that could have originated in the first instance of the universe. The axions would be so numerous and so dispersed that they would fill the entire cosmos like an invisible mist, exerting a subtle but constant gravitational influence. The existence of sterile neutrinos has also been proposed, an exotic version of known neutrinos, but even more evasive. They would not interact with anything except gravity. And other theorists have suggested that dark matter could be composed of supersymmetric particles not yet detected that would extend the laws of the standard model of physics. The experiments to find it are as impressive as they are fruitless. In underground laboratories in Italy, Japan, and the United States, cryogenic chambers the size of cathedrals are built, designed to detect the impact of a single particle of dark matter. Particle accelerators, such as the Large Hadron Collider, attempt to recreate the conditions of the early universe, searching for collisions that may reveal traces of these hypothetical particles. So far, the silence is absolute. No sign, no detection. And yet the gravitational evidence is still there. Galaxies spin too fast. Gravitational lensing shows invisible masses. The map of the cosmic microwave background reveals a structure that cannot be explained without its presence. Perhaps dark matter is not a particle, but a sign that our theories of gravity are incomplete. Some physicists propose radical modifications, such as the Mond theory or Milgram's modified gravity, that could explain the anomalies without resorting to invisible matter. But until proven otherwise, the cosmos appears to be leaning toward dark matter. We don't know what it is, but we do know what it is not. It is not light, it is not atoms, it is not antimatter. But what if dark matter doesn't actually exist? What if we are looking for a ghost? Not all scientists are convinced that dark matter exists. Although the gravitational evidence is strong, some believe that perhaps there is no invisible substance filling the universe, but that our laws of gravity may be incomplete. Perhaps what we observe is not a mystery of matter, but an error in the way we understand space and time. In 1983, Israeli physicist Mordechai Milgram proposed a bold idea. Perhaps gravity does not behave the same on galactic scales as it does in the solar system. His theory, called modified Newtonian dynamics, suggests that at extremely low accelerations, gravitational attraction declines more slowly than Newton's equations predict. If this were true, galaxies could maintain their shape without the need for invisible matter. For years, Mond managed to reproduce with surprising accuracy the galactic rotation curves that baffled astronomers. But it had a problem. It didn't explain large-scale phenomena, such as galaxy cluster formation or cosmic microwave background anisotropies. Later, Israeli physicist Jacob Bekenstein extended Milgram's idea to Einstein's relativistic framework, giving rise to TVS, tensor vector scalar gravity, a more complete version that incorporated the curvature of space-time. However, even this version faced difficulties in explaining precise observations such as those of the bullet cluster, where the mass measured by gravitational lensing does not match the visible matter. Other researchers have looked for answers in the quantum effects of the vacuum. In quantum mechanics, the vacuum isn't really empty. It's a seething sea of ephemeral particles that constantly appear and disappear. Some physicists propose that these fluctuations could generate additional, invisible, but real gravitational pressure that would alter the dynamics of the cosmos and give the illusion of dark matter. Extensions of general relativity that modify how gravity propagates through space have also been explored. In these versions, space-time itself could have emergent properties, behaving like an elastic fabric where energy and information are redistributed in ways not yet understood. Perhaps dark matter is not a substance, but a manifestation of that dynamic geometry. And more recently, even more radical theories have emerged. Some combine quantum gravity, holography, and thermodynamics. According to these ideas, gravity might not be a fundamental force, but a statistical effect derived from the information encoded in the universe. In that case, dark matter would be just an emergent consequence of the way space stores and processes information. All these hypotheses have one thing in common: doubt. They doubt that the universe needs an invisible component to explain its structure. But so far, none of them manages to replace the gravitational elegance of dark matter completely. Perhaps in the end, both visions are true. The universe could be composed of real shadows and of laws that we still do not understand. For now, we treat dark matter as real. Its gravitational fingerprints are everywhere, and its importance is so great that it is impossible to imagine a universe without it, since it not only explains things as they are now, but as they have been, and as they will be. In the first instance of the universe, shortly after the Big Bang, everything was a fiery soup of particles. Visible matter and radiation were so intertwined that light could not travel freely. The cosmos was opaque, a glow trapped in itself. But while baryonic matter, the matter that makes up atoms, mixed with energy, dark matter remained on the sidelines, separate, silent, oblivious to what was happening to ordinary matter. That separation was crucial. While radiation prevented ordinary matter from concentrating, dark matter was already beginning to form structures under the pull of its own gravity. Small fluctuations in density grew, attracting more and more invisible mass, until they became the first gravitational nodes in the universe. There, billions of years later, is where the first galaxies would form. In extensive cosmological simulations, such as the famous Millennium simulation, astrophysicists recreate this process with millions of dots representing dark matter. The result is overwhelming. A cosmic network that extends throughout the universe, made up of filaments and voids, like a colossal spider's web hundreds of millions of light-years across. Galaxies, clusters, and superclusters are located precisely at the nodes where these filaments intersect. Visible matter does not define the structure of the cosmos, it only reveals it. Authentic architecture is the work of dark matter. In that gravitational network, ordinary matter acts like dust that accumulates on an invisible sculpture. The gases fall into the centers of gravity, heat up, ignite, and thus stars are born. Without dark matter, galaxies could not have formed or remained stable. The universe would be a homogeneous fog, without structure or destiny. Even today, when we observe the sky, with the most powerful telescopes, we see the past written on that dark skeleton. Waves from the cosmic microwave background, the echo of the Big Bang, show the fingerprints of dark matter in their texture. Slight temperature variations that betray their gravitational influence more than 13 billion years ago. And on even larger scales, dark matter continues to guide the evolution of the universe. Galaxies orbit within giant, invisible halos, extending far beyond their luminous edges. Those halos protect them, maintain their cohesion, and determine how they collide or merge. In a way, dark matter doesn't just shape the cosmos, it rules it. Everything we see, from constellations to the most distant galaxies, is just the shallow glow of a much deeper structure. A universe of shadows that sustains the universe of light. And yet, even this invisible scaffolding is not the end of the story. Because if dark matter is what shapes the cosmos, another force pushes it to unravel. An energy that does not attract but drives apart. Dark energy. For much of the 20th century, astronomers believed they understood the fate of the universe. After Edwin Hubble discovered in 1929 that galaxies were receding from each other, evidence of cosmic expansion, scientists assumed that gravity would eventually slow that motion. They thought that gravity acted as a brake, since the matter filling the cosmos should gradually slow its own momentum. The image was logical and elegant. The universe, born in an initial expansion, spread out like a ball thrown upward. Over time, its speed would slow to a halt, and then it could collapse back upon itself in a big crunch. A great end of fire and density. But the universe, once again, defied our expectations. In the late 1990s, two teams of astronomers, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, decided to accurately measure the rate of cosmic expansion using Type 1a supernovae, stellar explosions so bright and uniform that they serve as standard candles for calculating astronomical distances. The standard candles are reference points for measuring distances in the universe. The idea was simple. If the universe was slowing down, distant supernovae should look brighter than expected. But something disconcerting happened. When comparing the measurements, the results were opposite to what was predicted. Distant supernovae were dimmer, not brighter. That could only mean one thing. The universe wasn't slowing down its expansion. It was speeding it up. The finding was so surprising that many thought it was wrong. But the data were repeated over and over again with different telescopes in different hemispheres and by different teams. There was no room for doubt. The universe was expanding faster and faster. Something invisible, a force contrary to gravity, was pushing space itself outward. And thus, the concept of dark energy was born, an unseen force rewriting the destiny of the cosmos and constitutes roughly 68% of the universe, making everything else, from stars to galaxies, a mere fraction. Matter, even dark matter, was not enough to explain this acceleration. There was an energy of the void, a cosmic thrust that overcame the attraction of all the masses combined. In 1917, Einstein introduced a similar idea, the cosmological constant, to preserve a static universe. A term was added to his equations to maintain a static universe. Decades later, that anti-gravitational force that he himself dismissed reappeared, not as a mistake, but as the key to accelerated expansion. The discovery of dark energy forever changed our view of the cosmos. If dark matter shapes the universe, dark energy propels it into the void. It is the silent force that stretches space, the invisible breath of the cosmos, whispering across eternity. The universe does not stop, it accelerates. And it does so faster and faster. But what is dark energy? Does it have anything to do with dark matter? Naming something is not always the same as understanding it. We name dark energy as the cause of cosmic acceleration, yet we have no idea what it truly is. We know what it does, push the space outwards, but we don't know how it does it, or why it exists, or what it is made of. Quantum physics also offers a tantalizing, if problematic, explanation. According to this theory, the vacuum is not really empty. It is a sea of fluctuating energy where virtual particles constantly appear and disappear. That vacuum energy should exert pressure on space, generating a repulsive force. The problem is that when physicists calculated the amount of energy that the vacuum should have, the result was so enormous it bordered on absurdity. 10 to the power of 120 times larger than what observations allow. It was quite literally the greatest discrepancy in the entire history of theoretical physics. If the vacuum had that much energy, the universe would have exploded instantly after the Big Bang. That monumental discrepancy, the so-called cosmological constant problem, reveals that we still don't fully understand how quantum mechanics and general relativity are related. On the scale of the tiny, the fluctuations of the void dominate. On the cosmic scale, the curvature of space-time dictates dynamics. But when we try to put the two descriptions together, the equations contradict each other. Some physicists propose that dark energy is not constant, but dynamic, a changing substance known as quintessence. In this view, the universe would be permeated by a slowly evolving energy field, altering the rate of expansion over time. Others suggest that dark energy could be the result of extra dimensions or a subtle curvature of spacetime that we cannot yet detect. Whatever it is, dark energy defies our categories. It is not light, nor matter, nor radiation. It is not antimatter, nor dark matter. It is the backdrop that sustains all existence, the invisible pressure that separates galaxies and defines the future of the cosmos. Einstein once tried to hold the universe still, yet dark energy compels it to move. Where is dark energy? Why can't we see it? Just as we can't see dark matter, we can see its gravitational influence. We can't see dark energy, but we can see its influence on the expansion of the universe. Today, we know that the universe is expanding and that it is doing so ever faster. But it's not that galaxies travel through space, but that space itself stretches, taking with it everything in it. Clusters, stars, galaxies, light, and time. At first, this expansion seemed slow and even, but the observations revealed something puzzling. The expansion is not only continuing, but accelerating. The distance between galaxies is increasing faster and faster, as if an invisible force were pushing the very fabric of the cosmos. That force is what we call dark energy. It does not act like gravity or any other known interaction. It does not pull, but separates. To test this, astronomers use three fundamental instruments. The first is Type 1a supernovae, which we have already discussed previously. These stellar explosions, as bright as entire galaxies, allow immense distances to be measured with precision. By comparing the observed luminosity with the expected luminosity, it was discovered that the universe stretches more than expected. The second instrument is the cosmic microwave background, the fossil radiation from the Big Bang. This faint glow, which permeates the entire sky, preserves the traces of the first fluctuations of the universe. By analyzing its temperature and distribution, scientists have been able to deduce the total density of the cosmos and determine that most of its energy comes from something that does not emit light: dark energy. The third method is the study of baryon acoustic oscillations, vestiges of pressure waves that race through the primitive plasma before atoms were formed. These waves left a measurable imprint on the distribution of today's galaxies, a kind of cosmic ruler that allows us to calculate how the expansion has changed over time. The results of these measurements coincide. The universe is expanding faster and faster. But dark energy not only alters the speed of expansion, but also the geometry of space-time. In a universe dominated by matter, space would be curved inward, like the surface of a sphere. In one dominated by dark energy, space tends to be flat or even hyperbolic, expanding without limits. According to measurements from the Planck satellite, the universe is almost perfectly flat, indicating that dark energy exerts a constant and uniform pressure in all directions. We live then in a cosmos that stretches endlessly. Every second, the space between galaxies increases. Every year, the most distant objects move away at speeds that are close to that of light. Someday, in the distant future, the most distant galaxies will disappear from the observable horizon. The universe will continue to expand, but we will no longer see its light. The only thing we can see are the stars of our own galaxy. Dark energy doesn't just shape the cosmos, it redraws its borders. But to what extent will it shape our universe in the future? The universe does not stop expanding, and in that expansion, its destiny is written. Every new observation, every measurement of dark energy is an attempt to decipher the end of it all. Will this acceleration ever stop? Or will the cosmos continue to stretch into oblivion? There are three grand visions of the cosmic future, three outcomes that science contemplates with amazement and vertigo: the Big Freeze, the Big Crunch, and the Big Rip. The Big Freeze is the most widely accepted scenario today. If dark energy maintains its current intensity, the expansion will continue indefinitely. The galaxies will move away from each other until they disappear from the visible horizon. 100 billion years from now, the Milky Way and its closest neighbors will be the only lights in a darkening sky. Over time, even stars will die, becoming white dwarfs. And then black dwarfs, cold stars that no longer emit light. the temperature of the universe will fall until it approaches absolute zero. No physical process will be able to continue. It will be a universe without contrast, without movement, an icy eternity. The second scenario, the Big Crunch, is its opposite. If dark energy ever slows down or changes signs, gravity could regain control and stop the expansion. Galaxies would begin to get closer, clusters would collapse, and space would compress. The entire universe, with its billions of galaxies, would end up folding in on itself in a colossal implosion. Temperatures would rise to unimaginable levels, and matter would return to the primitive plasma state of the Big Bang. Some theorists imagine that this end could give rise to a new universe, a cosmic cycle with no beginning or end. The third scenario is the most disturbing. The Big Rip, or Great Tearing. If dark energy is not only maintained, but also increases over time, its strength could overcome all gravitational resistance. First, it would separate the galaxies, then the stars, then the planets, and finally, the atoms themselves. In a final instant, even space-time would fragment, erasing all structure from the universe. It would be absolute dissolution, the end of geometry, time, and matter. No one knows which of these futures awaits us. It all depends on the ultimate nature of dark energy, whether it is constant, changing, or illusory. What we do know is that the universe is no longer a static or eternal place. It is alive, in perpetual motion, destined to be transformed. Perhaps, like every story, the cosmos also has an end, but even that end would be part of a larger cycle, a cosmic breath that expands, contracts, and starts again. The universe, like us, was born out of the void and will die in it. But how empty is the vacuum really? After a century of observations, simulations, and theories, the universe can be summed up in three fundamental components. A tiny fraction, just 4.9%, is baryonic matter, the standard stuff that stars, planets, bodies, and the antimatter that accompanies them are made of. About 27% is dark matter, that invisible substance that provides the gravitational scaffolding of the cosmos. But the most overwhelming component is dark energy, which accounts for nearly 68% of the universe and dominates its evolution. In turn, 99% of the 4.9% of baryonic matter is plasma, and only the tiny 1% of that baryonic matter is solid, liquid, and gaseous matter like that which makes us up. That is, only 0.049% of the universe, less than a 10,000th part, can give rise to life as we know it. In other words, everything we can see and touch constitutes only a tiny fraction of reality. The rest is made of something we don't understand, but which governs the fate of everything. It is intriguing that despite being the most abundant, we have hardly any idea what dark energy may be. To better understand it, scientists have designed some of the most ambitious experiments in the history of physics. The Dark Energy Survey in Chile observed the light from more than 300 million galaxies for 6 years to map how matter is distributed on a large scale. The European Space Agency's Euclid project, launched in 2023, seeks to reconstruct the geometry of the cosmos by measuring the shape and distance of tens of billions of galaxies. The Vera Rubin telescope, under construction in the Chilean Andes, will repeat the observation of the entire southern sky every few nights to detect how the expansion evolves in real time. Other experiments, such as the Dark Energy Spectroscopic Instrument in the United States, measure the redshift of distant galaxies to calculate the rate of cosmic expansion with a precision never before achieved. Everyone is seeking the same answer: whether dark energy is truly a constant or if it varies over time. The mystery remains, but studying it has revealed a more profound truth. The universe is, for the most part, empty. Not a dead void, but an active, dynamic void, full of energy and potential. What we call nothing is, in reality, the very fabric of the whole. And yet, from that emptiness, something more than matter or energy was born. Consciousness was born. For centuries, physics described the universe in terms of matter and energy. Everything that exists, from atoms to galaxies, seemed to be able to be explained as combinations of these two realities. But in recent decades, a new idea has begun to transform that view. The universe is also made of information. Information is not just an abstract concept or a human invention. It is a physical ingredient as fundamental as mass or light. Every particle, every field, every natural process stores and transmits information. The physicist John Archibald Wheeler, a disciple of Einstein, expressed it with a phrase that is quoted today in all modern cosmology treatises: "It from bit," which means that everything that exists comes from a bit of information. The universe would be, at its deepest level, a gigantic cosmic processor that transforms data into reality. This principle appears in unexpected places. For example, the second law of thermodynamics states that entropy, disorder, continuously increases. Every time a system is transformed, it loses some of its valuable energy, but it also generates information about its own state. In fact, entropy and information are two sides of the same coin. The more disorder a system has, the more information it contains about its possible evolution. Even black holes, those abysses where nothing escapes, obey this rule. In the 1970s, Stephen Hawking and Jacob Bekenstein discovered that black holes are not entirely black. They emit mild radiation and have an entropy proportional to the surface of their event horizon. In other words, the area of a black hole encodes information about everything that has fallen into it. That observation gave rise to the holographic principle, according to which the entire universe could be described as a three-dimensional projection of the information contained at its boundary. Today, physicists are exploring the possibility that space-time itself arises from quantum information, entanglements of particles that define the geometry of the cosmos. According to this view, reality would not be a scenario where events occur, but the emerging result of the information that those events contain. If matter is what forms and energy that drives, information is what organizes. It is the invisible code that transforms chaos into structure, chance into law. From galaxies that follow fractal patterns to DNA that builds a living being, the entire universe seems to be governed by the same principle. Nature processes information to understand itself. So, if the universe not only exists, but also communicates with itself. In this sense, what structures would be the best to fulfill this purpose? What kind of matter could communicate, study, and observe itself? The answer is life. For billions of years, the matter of the universe was just that: dust, gas, rock, and fire. But in some places, under the right conditions, something extraordinary happened. Chemistry began to organize itself. Atoms, obeying the same physical laws that govern stars, began to combine into increasingly complex shapes. Among all the elements that the cosmos manufactured in the stars, one stood out for its versatility: carbon. Capable of forming chains, rings, and stable three-dimensional structures, carbon became the basis of a new stage of the universe: life. Alongside it, water acted as a perfect medium. It dissolved substances, facilitated chemical reactions, and offered a flexible environment where molecules could meet and replicate. From the interaction between carbon, oxygen, hydrogen, and nitrogen, the first self-replicating systems emerged. There was no intention, only physics and probability. But over time, molecular evolution became biological. Molecules became cells, cells became organisms, and matter, for the first time, began to sense and react. On Earth, that process took more than 3 billion years through a sequence of mutations, catastrophes, and adaptations. Life diversified in unimaginable ways. But the most amazing leap came much later, when a group of primates began to develop brains capable of not only perceiving the world, but thinking about it. The human brain is, as far as we know, the most complex structure in the observable universe. It contains about 86 billion neurons, each with thousands of synaptic connections, forming a network with several links comparable to the number of stars in the galaxy. Inside, electrical impulses travel at speeds of up to 400 kilometers per hour, generating thoughts, emotions, and memories. Everything we think of as me is nothing more than a dynamic pattern of organized matter. Paradoxically, this structure of neurons and synapses resembles the cosmic webs that connect galaxies. In both, the distribution of matter follows fractal patterns, as if the universe were repeating its architecture at different scales. A brain, in a sense, is a universe that thinks of itself in miniature. Consciousness, that spark that allows us to observe the world and wonder about our origin, is perhaps the greatest act of self-exploration of the cosmos. It did not arise by chance. It is the inevitable consequence of a universe that tends to complexity, that seeks to organize its own information. Thus matter, after billions of years of evolution, learned to contemplate itself. The carbon that once burned in the heart of a star now reflects on the stars that gave rise to it. Could it be then that life was not formed by chance, but rather that this is the final destiny of matter? Is life the fourth component of the universe, along with matter, and dark energy? Of everything that exists in the universe, only a tiny fraction is made of the same matter as us. 0.049% of the cosmos, less than a 10,000th of all that there is, corresponds to the baryonic matter that can form life. An amount so minuscule that it would seem irrelevant. But that fraction, that tiny remnant of luminous matter, is enough to fill billions of worlds with oceans, atmospheres, and complex chemistry. Life, in cosmic terms, is an improbable phenomenon, and yet inevitable. Wherever the right conditions are in place, a source of energy, stable molecules, a protective environment, matter begins to organize, to copy itself, to learn. It has done so on Earth, and it probably will, or has already done so, or is doing so, in many other places in the universe. Carbon, born in the bowels of stars, is the pillar of biology as we know it. But life might not be limited to him. On other worlds, silicon-based organisms could exist, where the rock is flesh, or beings that breathe ammonia, that swim in liquid methane, or even that exist as plasma structures, patterns of energy sustained by magnetic fields. As alive as they are ephemeral, beings that live in the heart of the stars, with forms and natures so strange that under our understanding and limited knowledge, they could not be classified as life forms. If life is a form that matter takes to perpetuate information, then the universe could be full of life, only not all of it looks like us. Still, as Neil deGrasse Tyson said, you don't need to imagine exotic life forms made of plasma or anything else. Carbon-based life forms can be so diverse that 0.049% is more than enough to create millions of conscious forms. From microscopic bacteria to intelligences capable of reflecting on their origin. We are the product of that tiny portion of the universe that managed to escape equilibrium, that dared to evolve towards complexity. And in that complexity, life plays an unexpected role. It doesn't alter the laws of physics or compete with dark matter or dark energy, but it does add something new: meaning. Life doesn't just obey the laws of the universe, it interprets them. It is the point at which matter ceases to be observed and becomes an observer. Perhaps the universe did not create life as an accident, but as a way of becoming aware of itself, a way of translating its vastness into thought. In this way, dark energy drives the cosmos toward expansion. Dark matter gives it shape. Baryonic matter gives it body. And life, finally, gives it consciousness. But behind all of that, in the space that binds every particle, every galaxy, and every thought together, there seems to be something else. Not a fifth element, but an underlying dimension that connects all the others. Information. For years, some scientists have theorized that information could be as fundamental as matter or energy. It is not a residue of human thought, but a physical property of the cosmos. In quantum physics, every interaction, every collision of particles involves an exchange of information. Nothing is destroyed. It is only transformed or coded in another way. Quantum entanglement reveals the strange nature of this informational fabric. When two particles become entangled, their states remain connected, no matter the distance. If one is measured, the other responds instantaneously, even if it is light years away. There are no traveling signals, no traditional communication. Simply, the universe knows its own state in real time. It is as if the information were distributed, not in the objects, but in the space that unites them. Could it be that dark matter and dark energy are somehow related? Under that premise, some theorists have proposed that dark matter and dark energy could be distinct manifestations of a universal informational field, a sea of information that underpins physical structures. In this view, ordinary matter would be only the local crystallization of that field, the result of a temporal organization of cosmic data. Quantum decoherence, on the other hand, reminds us that observable reality only arises when quantum information collapses when interacting with an observer. This process, the passage from the possible to the real, is also an act of information. Perhaps consciousness, more than a biological exception, is an inevitable consequence of a universe that processes information at all levels. If dark energy drives the expansion and dark matter sustains the structure, the information could be what keeps the whole coherent. And consciousness, that form of self-referential information, would be the last step in that chain, where the cosmos not only exists, but perceives itself. The vacuum, then, is not the absence of matter or energy. It is the pure presence of potential information, the field where the laws of the universe right themselves. There, in that quantum silence, gravity, energy, light, and thought are born. Perhaps in the end, everything we call reality is nothing more than information interpreting itself. The universe began without eyes to see itself, without a mind to think about itself. It was just expansion, energy, and silence. For millions of years, matter and light mixed in a fiery, formless, purposeless ocean. Until, little by little, chaos was organized. First came dark energy, the force that drives space and sets the pace of the cosmos. Without it, the universe would not breathe. It is the silent engine that stretches the nothingness and gives rise to the whole. Later, dark matter wove the invisible skeleton of creation. We do not see it, but its gravity draws the roots along which galaxies, clusters, and suns will move. It is the architecture that supports the visible universe, the scaffolding on which luminous matter accumulates like dust on an invisible thread. From that dust was born baryonic matter, tangible substance, atoms, antimatter, stars, and planets. With her, the universe learned to build. And in one corner, a tiny fraction learned something new: to organize, replicate, and think. From that remnant, life was born. Life is not an exception to the laws of the cosmos. It is their consequence. It is complex baryonic matter following the same expansion impulse that guides dark energy. Where there is life, the universe densifies in meaning. Where there is consciousness, it is reflected. But among all these levels, energy, matter, life, there is a common principle: information. It is the invisible current that unites the great with the small, the physical with the mental. Information enables galaxies to spin, atoms to form, and brains to think. In every particle, in every thought, the universe stores something of itself. Consciousness, then, is not a biological anomaly. It is the most complex echo of that universal information. When we think, the cosmos thinks. When we observe, the universe observes itself. We are a way in which reality is recognized. From expansion to form, from matter to thought, the universe has traveled a 13.8 billion-year path to get here. To the moment when an infinitesimal part of itself wonders what it is made of. Perhaps the universe is not looking for an answer, but for the question itself. Because when he questions himself, he stays awake. The cosmos did not end with the formation of stars or with the appearance of life. It continues to expand in every look, in every idea, in every atom that remembers having been light. The universe began without eyes, and today it is looked at. It began without ears, and today it is heard. It began without a mind, and today, after billions of years, it is beginning to know itself and understand what it is made of.